So far we've discussed how to perform linear calibrations and how to estimate the uncertainty associated with those linear calibrations. So what's the big deal about those linear calibrations? Well, the procedures that we've learned are related to these common instrumentation terms that you'll hear as engineers. Those common terms are, some of those common terms are span, range, and operating limits or operation limits. All three of these terms mean the same thing. And basically, those are fancy ways of saying these are the range of input values that the instrument was designed to measure and provide reliable output for. So for the load cells that were used in Engineering 212, those were 10-pound load cells. They had a designated span or range or operation limits of 10 pounds either in compression or in tension. Different thermocouples or temperature measuring devices have ranges of temperatures over which they're designed to provide reliable output measurements. Same thing goes with any transducer that we're going to work with. They're going to have a specified range of operation. Another common term is sensitivity. Now, sensitivity tells us about how much the output of the instrument is going to change per unit of input. So, how many volts, what is the change in the voltage going to be per each pound of force that we apply to the load cell? Or what is the output voltage, how is the output voltage going to change when we increase the temperature by 1 degree for a temperature measurement device, so on and so forth. And the sensitivity can be determined from the slope of the calibration line, because the slope of the calibration line tells us about the how quickly the output is going to change relative to the input. This is also related to resolution. Resolution is the minimum change in the input that can be reliably measured by the instrument. So both the sensitivity, the slope of the calibration line, as well as the uncertainty about that calibration line determine our resolution. So if we cannot see a significant change in the output voltage of our load cell by adding just a few tenths of a pound to our load cell, that defines our resolution, in that we need to increase the load by more than a tenth of a pound, for example, to be able to see an appreciable change in the output. All right, and then the calibration line and the uncertainty also play into these common instrumentation terms, which are measurement uncertainty, which are accuracy and precision. Sometimes we use these terms interchangeably, but actually they have precise definitions that we need to discuss. So when we talk about looking at the uncertainty or the spread in the data or in our confidence intervals, we're really talking about imprecision, which is the lack of precision. So the standard uncertainty or uncertainty with a confidence interval is really a measure of imprecision. Okay, and it's measured by the standard deviation of multiple measurements, or the standard deviation multiplied by the t-value, so that we can get a confidence interval. So an imprecise instrument will not provide reliable readings. All right, so basically what that means is each time that I apply the same input, I'm going to get a wide variability in the output of the instrument. The readings are not going to be grouped together well. Okay, and accuracy is the second term. Accuracy tells us how close the instrument measurement is to the actual value that's being measured. So this is also called a bias error. And the important thing about this is that accuracy errors can be removed by proper calibration of an instrument. Imprecision, we'll talk about this a little bit more, imprecision cannot be removed, but inaccuracies can be removed by proper calibration. Now, just want you to note that these two terms are often confused and misused, so we're going to spend just a little bit more time. And there are two examples, or two sort of visual ways to describe this. One is using the bullseye. Okay, an instrument that is both accurate and precise will hit the bullseye all the time, and we'll have a nice tight grouping around that bullseye. This right here, the second target, is an example of a device or a transducer that has low accuracy but very high precision. The low accuracy is that we're not hitting the bullseye, we're not getting the exact value of the measurement that we're trying to make, but all of the readings are grouped closely together. So this would be a constant offset. Say we measure an ice water bath with a thermocouple, and it always comes up to be 2 degrees Celsius. Well, we know that that ice water bath should be close to 0 degrees, so we have high precision in our measurement, but we have low accuracy. All right, the third target here represents a high accuracy, low precision. All our measurements are scattered around the bullseye, but none of them are actually hitting the target. But if we were to average all of these, we would see that they come close to being weighted in the center of the target. So we have high accuracy because all of our measurements are near what they should be, but the precision is low because there's a lot of scatter in the measurements. And of course, this represents both low accuracy and low precision. Another way to look at this is using our standard bell curve, our Gaussian distribution. All of the information that we receive from an instrument can be described by this bell curve. We have a high probability of our instrument output being near the mean, and we have some spread about that mean. Now let's see the actual value, the measurand value that we would like to actually measure is over here somewhere. Okay, so the actual value of our ice water is 0 degrees, but we're measuring, say, 2 degrees Celsius. That offset represents really the inaccuracy in the system. Right, where the difference between the reference value and the mean of all of the measurements represents the accuracy, and the precision is represented by the width of the bell curve, the standard deviation of that Gaussian distribution about that mean. Okay, so you can see that if we can properly quantify using our instrument calibration, we can remove inaccuracies from the system, but we cannot remove imprecisions from the system. Okay, so some other ways to sum that up is that accuracy tells us how well the output relates to the actual input, and again, through proper calibration, we can remove this inaccuracy, which is called a bias error, or a constant offset in the measurement. It's the difference between the measurement that we receive and the known standard value. So an inaccuracy is the average measurement minus the known standard value, and it's represented by the intercept of the calibration line, the B component of our line of best fit. Now, precision tells us how closely repeated measurements of the output are related when the same input is provided. So this represents random uncertainties, scatter, or noise in the data that cannot be removed from the system. All right, so we can remove accuracies or bias errors by subtracting out the intercept from our calibration line. But random uncertainties affect our precision, and our precision cannot change in a system. It's defined by the characteristics of the measurement system. All right, so in practice, calibrations may not necessarily be practical. So for example, our multimeters are measurement tools, and they have to be calibrated, but they come factory calibrated. We don't have the tools in hand to be able to properly calibrate those multimeters. Often, what we have to do is we have to rely on manufacturer specifications, but they're not always clear in their statements of accuracy or imprecision, and usually they don't tell us the stated confidence interval. Oftentimes, it'll be a single number that represents the largest expected uncertainty. Sometimes it will be the uncertainty relative to a reading, so it might be a percentage of the reading, or it may be some combination of these. And again, usually they're not stated with confidence, so we assume that it's going to be a worst case or the largest expected uncertainty. Right? So for example, if we take a look at our Fluke 179 multimeter and its accuracy for reading DC voltages, we'll find that it has an accuracy of plus or minus 0.09% plus 2 counts. And I'll show you where we find that. If we look at the digital multimeter manual, down towards the end of the document, we see this chart which tells us all of the resolution information and the accuracy for different settings and for different measurements that we can make. So we're interested in the voltage, the DC voltage, and we're using the model 179. So if we come over to the DC voltage in the model 179, we see that there are a couple of different ranges that we can use. And what these ranges represent are the maximum value within a given measurement range. So if we're reading a voltage that is less than 6 volts, we will have a resolution of thousandth of a volt, which would be a millivolt. If we're reading something that's less than 60 volts, we have 10 millivolts resolution. If we read something that's less than 600 volts, we'll have that's less than 600 volts but more than 60 volts. We will have a tenth of a volt resolution, so on and so forth. But for all three of these, we see that the accuracy is stated in the same way. We have 0.9% of the reading plus 2 counts, and those 2 counts refer to the resolution. All right, so for every reading that we make, we're going to have to take the reading, multiply it by 0.09%, and then add 2 times the resolution in the particular range that we're operating to come up with the uncertainty. Okay, so what we're going to do is go back to this example right here. All right, we look at the, again, the accuracy is given, and we're assuming that we're going to read a voltage that is less than 6 volts. All right, so let's determine what the uncertainty of the reading will be when it measures exactly 0 volts, 0.000. All right, well, if we multiply our 0 volt output by the 0.09%, anything times 0 is 0. So that component of the uncertainty is 0, and then we have to add in the 2 counts of uncertainty, which correspond to our resolution. The 2 counts of the uncertainty, which correspond to the resolution, will give us 2 millivolts. Therefore, the uncertainty in the reading when it measures exactly 0 volts is 0 volts plus or minus 0.002, or plus or minus 2 millivolts. Similarly, if we were to look at the uncertainty of the reading when it measures 4.621 volts, we would apply a similar calculation. Okay, so again, we assume that we have a reading of 4.621 volts. That's going to be our nominal output, right? And remember that we have an inaccuracy or uncertainty of 0.09%. Okay, so that uncertainty can be calculated by multiplying 4.621 volts by 0.0009. And when I run that calculation, I get 0.00416 volts. All right, and then I have to account for my 2 counts. All right, so my 2 counts is going to be 0.002 volts. So I add those two together, and my total uncertainty is going to be 0.00616 volts, or 6.16 millivolts. All right, so the way that we would state this measurement based on the uncertainties that we have in our multimeter would be 4.621 volts plus or minus 0.0062 volts. Okay, and what I did, I rounded there so that we would be close to the number to a similar number of significant figures for our reading. And if we look back at our PowerPoint here, what we could do is we could actually round that off as well, because we don't really need that last digit there. Okay, so that's how we can use the information in our multimeter manuals and how we can interpret the uncertainties given with common instruments.